Hi, welcome to NASA Launchpad. I'm your host, Amber Whalen. Do you remember when we talked about the solid rocket boosters, or SRBs, on the space shuttle, and we left you on a cliffhanger just 2 minutes into flight? Well, you don't have to wait any longer because we're going to dive into the SSMEs and external tank right here, right now on NASA Launchpad. Okay, first thing first, what is an SSME? Well, SSME stands for Space Shuttle Main Engine. So, if you're looking at the back of the Space Shuttle orbiter, those 3 engine nozzles you see there are attached to, or actually a part of, the main engines, the SSMEs. Now, let's do a little comparing and contrasting with the SRBs, shall we? The SRBs are separate rockets that are attached to the shuttle system and are jettisoned during the flight, while the SSMEs are built into the shuttle orbiter. The SRBs are much more powerful than the SSMEs. They provide 71% of the thrust from liftoff to SRB separation, up to 3.1 million pounds of thrust. Each shuttle main engine has only 400,000 pounds of thrust. So, the solid fuel in the SRB is generally more powerful, but it does have its disadvantages. For one thing, it's virtually impossible to adjust the amount of energy given off by the solid fuel once it's ignited. But with liquid propellant, like in a car, it's easier to control how much fuel is going into the engine, which in turn lets you control how fast the vehicle goes. But unlike a car, the SSMEs don't use regular unleaded or even diesel fuel. They actually burn liquid hydrogen and liquid oxygen, which are supplied by the space shuttle's external tank. That's the big orange part of the shuttle transportation system. And I do mean big. The space shuttle engines collectively burn 3,917 liters of liquid propellant per second. Just to put that into perspective, if the shuttle engine burned water instead of liquid hydrogen and liquid oxygen, the amount of fuel that could fill an average-sized swimming pool would be drained in only 25 seconds. The space shuttle engines are designed to perform in extreme temperatures. When icy cold liquid hydrogen is burned with liquid oxygen, the temperature inside the combustion chamber reaches an incredible 3,300 degrees Celsius. That's higher than the boiling point of iron. No wonder the 3.2-ton engines are taken to the space shuttle main engine processing facility after every flight and inspected to see if any parts need to be replaced before the next mission. And just how powerful are hydrogen and oxygen as fuel sources? Well, here with the demonstration is Dr. Richard Biles of the Virginia Air and Space Center. And do I really have to say it? Don't try this at home.
So now we have a hydrogen balloon. That's the balloon we filled up with a little bit of oxygen and the rest hydrogen. And hydrogen is lighter than air gas and is one of the gases that makes the shuttle go. And its main tank is full of liquid hydrogen and liquid oxygen. And that's just, they're really compressed. So when they meet together down at the bottom, they fire. So I just wanted to show you what hydrogen does when you light it.
Big boom, right? Actually, rockets are just controlled explosions. So while our little demonstration may not be exactly what happens with the shuttle, it does show you the kind of energy that hydrogen is capable of generating. If a little balloon filled with hydrogen has that kind of energy, imagine how much potential energy is stored in the massive 550,000 liter or 146,000 gallon external tank. But obviously, all that energy isn't released at one time. It's gradually released through a series of vents and valves, allowing for controlled explosions, letting NASA control how fast the shuttle travels. Now, you know that the SRBs, after their fuel is expended, separate from the shuttle and fall back down into the ocean, where they are retrieved for reuse. But the external tank stays with the shuttle until it's almost in orbit, so it has to come back down through the atmosphere at a high speed. This causes it to break apart, so it's unable to be reused. However, the external tank technology is being reused in a different sense. You know that the Space Shuttle program is scheduled to end in 2010, and the shuttles, which served as a workhorse for the space agency, will be retired. And what's coming next? That's right, the Constellation program. If you look closely at the Ares 5 rocket, you might notice something very familiar. That big orange section right there in the middle? Yeah, that's the core propulsion stage, which is, as you can probably guess, derived from the space shuttle's external tank. Sure, it's been modified, but isn't that what it's all about? Learning from experience of the past and putting that knowledge to good use in the present and future? Sounds like a good idea to me anyway. All right, that's all the time we've got for now. Until next time, I'm Amber Whalen. Thanks for watching NASA Launchpad.